negative 15, and then it went, and at 0 Celsius, there was a phase change. And then we had, starting at 25 Celsius, we had some water. And we had some aluminum at 80 Celsius. And we had, so I draw the phase changes that possibly can happen. Was it 102, the steam? 102 Celsius. Okay, so then we drew the equation, the heat lost by steam is equal to heat gained by all the other stuff, the ice, water, aluminum. By the way, the symbol for heat often is interchangeable. The two most common symbols that we use is the H or the Q. So you see that those kind of interchangeably used, MC delta T. And then you can say H equals Q. And then for when something melts, we write down MLF for melting. And then the other one is for boiling. So this means heat of vaporization, and then heat of, fusion, and then vaporization. So this is melting, and then this is boiling. And of course, opposite of melting is freezing, and then opposite of boiling is condensation. Okay, so after we did that, we left with this big long equation. We multiplied everything in, and then I said, let's solve it on Wednesday. So let's see, does someone have the notes where we left off? Okay, so we've got this 1.996 times, we distribute that in, times 2 plus 539 times 4.184 plus 4.184 times 100 minus 4.184 TF. So remember, we used the specific heats, the heat of fusions, anything that was in calories per gram, we converted to joules per gram, so that everything will be joules. Plus wow. Yeah. Okay. Thank you. So then we just multiply all that out. Yeah.
Just as a reminder, where did those two melting and boiling point equations come from?
The melting, these ones?
Yeah.
Oh, this one was when a phase change happens. This is saying that the amount of heat that you put in goes into melting, and then the LF for water is 79.6 calories per gram. So let's say, for example, you have water or ice, let's say. So let's say you have 10 grams of ice. So what that means is how much, if we want to know how much heat does it take to melt 10 grams of ice. So then this equation says, okay, Okay, take how many grams of ice you have, and then multiply it by the heat of fusion per gram of ice. Then gram cancel. So the units are such that whenever you multiply these, you should get units of energy. So this is calories per gram. So the heat of fusion, the units is calories per gram or joules per gram or joules per kilogram or food calories per kilogram. As long as the top unit is energy and the bottom unit is mass. See? But the units of specific heat are slightly different. It has to be units of joules per gram per Celsius. See, this one doesn't have Celsius on the bottom. Why? Because when you're having a phase change, you're not experiencing a temperature difference. You're staying at the same temperature, and you're just going from one solid to liquid, so there's no temperature change. So this one and this one doesn't have a delta T. You see the difference? But for specific heat, the unit has to be calories per gram per Celsius, because unit change of temperature you need, you see? So that's a good question that you asked, which allowed me to explain this in even more detail. Okay, so now after we multiply all this out, let's see, what do we get here? Maybe what we could do is combine like terms here, anything that doesn't have T in it. 1.996 times 2 plus 539 times 4.184 plus 418.4. So anything that doesn't have a T, I'll just combine them. 2,677.568 minus 4.184 T final. Okay, so now I'm gonna combine this, not this, and then just this and this. So just even putting a check mark like that allows me to make less mistakes, so I can keep track of what I'm doing, you know, so visually I can see it. I'm combining that, and that. So then minus 50 times 4.184 times 25 minus 7200. Oh, that came out negative, huh? This one, these numbers were bigger. So it came out negative 51284.304. Okay, now we combine this, and this, you see. So I use a different symbol, like I might put a check mark on those, and then this I'll circle, you know, or I could do a square, just to signify that I'm combining these, you know, the squares, I'm combining the squares and I'm combining the circles, you know. Because this problem is more a matter of accounting for all the heat changes, combining like terms, and so even though mathematically it's not hard, there's no integration involved, there's nothing like that, but it's just, you can make a simple algebraic mistake which throws off your answer way off, you know. So now you have 20 times 4.184 plus 50 times 4.184 plus 90. Okay, so 382.88 TF. Okay, after that, it's pretty easy. Just move this to there, right? So add 5128.304. Which gives me 2677.
20.16.
Huh?
20.16.
20?
That's what I'm getting, but it could be wrong.
5,000 plus 2?
No, I meent the actual final.
Oh, okay, yeah. Let's go step by step so we can write it all down. 2677.568 plus 5128. So 7805.872. And of course add 4.184 to the other side. 382.88 plus 4.18. Okay, after that, just divide by this. So this is 7,805. Okay, let's see here. Oh, 20. Wow. So what does that mean? That means that the ice went and melted and went up and then just stopped here. That means water cooled, aluminum cooled, the steam came, had phase change, and then cooled all the way down to 20. Everything went down to 20. So is that answer legitimate, or do I have to now restart? Because when I started the problem, I assumed the final temperature was somewhere in this range, right? So is that answer legitimate, or do I have to reset everything up and redo it? So in other words, everything here lost heat, and only the ice was the one gaining heat. The cool thing about this is that the answer is legitimate. I don't have to redo it. So in other words, if you put this TF here into the original, remember how we set up the problem? We said heat gained by, we assumed that everything was gaining heat. Water was gaining heat, aluminum was gaining heat. We put mass of water, specific heat of water, TF minus 25. Plus aluminum was gaining heat, mass of aluminum, specific heat of aluminum, TF minus 80. And then ice was gaining heat, and then so on, right? So now, if you go back and put 20 into TF, what's gonna happen? 20 minus 25, it's gonna be negative. So that means negative gaining heat is the same thing as losing heat, you see? So it doesn't mean that this answer is illegitimate, you know? When you go here, you get a negative, it just means that now you're losing heat. So everything that you thought was gaining positive heat is actually gaining negative heat, which means it's actually losing heat. So you don't have to go back and redo the problem from the beginning. So that's it, that is the final answer. So in a calorimetry problem, the conclusion is you can assume the final answer to be somewhere. I could have assumed it to be between water and aluminum, somewhere here. Then set up my problem so that the ice is gaining heat, the water gaining heat, aluminum losing, steam losing. And then the answer might come out over here, which still is okay. It might come out over here. It still is okay. The only time you have to go back and redo the problem is when? If the answer comes out where? If the answer comes out greater than 100 or less than 0. If it comes out, I don't think it will ever come out less than -15. That'll be weird if it comes out. That means you just did an algebraic mistake, you know. And it shouldn't come out more than 102. That means you did some algebraic mistake, right? If it comes out more than this guy, you did something wrong. You did algebra mistake. And then if it comes below -15, you also did algebra mistake. But what if it comes over here? Or if it comes out here? Between 100 and the steam, or between 0 and -15. What if it comes out there? It still might be possible that it's a simple algebra mistake you made, you see. In which case you just have to kind of go back and look, oh, okay, is it an algebra mistake? Then you say, no, I've checked it and there's nothing wrong that I did. So then the conclusion is, maybe you had too much ice in that thrown into the mix. And so everything actually came. So if the answer that you got is here, it could be that you don't have a lot of aluminum, you don't have a lot of water, and you have very little steam. So everything has to come, and maybe what's gonna happen is that you really don't know what's gonna happen. The scenario might be that everything comes and then gets here, and the ice goes here, and maybe they meet in the middle somewhere here at 0, or maybe the answer is here. So you have to redo the problem. Or maybe you have too much steam. Maybe you get an answer between 100 and 102. Then you have to redo the problem all over again. Find out what's happening there. What if you get an answer that's 100? You might, that's very weird that you would get exactly 100 or 0. If you get exactly 0 and 100, you have to redo the problem. Okay, so anything, if you get anything less or the same as 0 and greater or the same as -15, I don't think it should come out equal to -15. If you get anything greater than -15, less or the same as 0, redo the problem. Or if you get anything greater or the same as 100, and then less than 102, redo the problem. Okay? So, so what do I mean here? At the beginning, how many grams of ice did we start with?
20.
20? Okay, let's just say I change the scenario up. And you know what we could do? We could even do it where we're not even simplifying the equation. We just have big long equation and we put it into our solver function. So that when we're playing around with the problem, we don't have to keep distributing it. Let's just have one big long solver equation and say, what would happen if we have this much mass of ice? What would happen if we had this much mass of steam? This much aluminum, we just put it in the solver and the solver spits out the answer for us. That's even better. So we just say mass of ice, specific heat of ice. The change in temperature is 15, right? So plus mass of ice, heat of fusion of ice, right? So I'm going back to my original equation that I had, the thing that we started with, plus mass of ice, because remember when the ice melts, it turns into water. Don't forget that. So you need mass of ice, specific heat of water, times what? The change in temperature is TF minus 0, right? TF minus 0. So for those of you who weren't here on Monday when we were doing this problem, this is a good jump in air time for you, because you didn't see the problem. So this is how we began the problem. We said we have to warm the ice, melt it, increase its temperature to TF, then we have to increase the temperature of the mass of the water, specific heat of water, and then water started out with 25, so we did TF minus 25. Then we did mass of aluminum, specific heat of aluminum, TF minus 80, right? And then that's equal to mass of the steam specific heat of steam, the change in temperature of the steam is from what? 102 to 100, so that's 2, right? Plus mass of steam, heat of fusion of steam, which is what? 539. Oh, but then we have to change that to what? So let's put in the heat of fusion of ice, 79.6. Here we have to put 53.9, but we changed that to joules, right? So we multiply it by 4.184, and then we change this to 4.184, right? And then we added what? Well, once the steam condenses, we have to then cool it down to TF, right? So then we did mass of steam, specific heat of steam, no, not steam, water. And then, what is that? So then we went from 100 to TF, right? And remember, we wrote it as 100 minus TF so that it's positive. Okay, so now this way of doing it, here's what I'm gonna do. I'm not even gonna simplify it. I'm just gonna write down the masses we had. Mass of ice was what? In our case was it 20?
Yes.
Okay, 20 specific heat of ice was what? I believe I gave it as a joule. 1. Was it 1.996 or 2 point? I think it was 2.108. So that one is already in joules, so I don't need to multiply by 4.184. Right? So then times 15 plus mass of ice times 79.6 times 4.184 plus mass of ice 20 times specific heat of water is 4.184 times TF plus mass of water was what? 50 times specific heat of water times TF minus 25 plus mass of aluminum was what?
100.
Specific heat of aluminum was 0.9, and that was already in joules, right? Yeah. TF minus 80 is mass of steam was
1 gram.
1 gram. Specific heat of steam was, oh, that's the one that's 1.996. So it's slightly easier to change the temperature of steam than ice. But water is twice ice, right? So then 2 plus mass of steam, heat of vaporization, times this, plus mass of steam, 1, times specific heat of water, times 100 minus TF. Okay, so now, let's go to our solvers. And put that big long equation. So this way of doing it, you're just putting the equation as is, 22.1
50.
50? Okay. How much aluminum was there?
100.
And then, 0.9. Equals 2 grams of steam.
1.
It's gonna be specific heat of steam, 1.996 times 2. Was it 2 grams of steam?
1.
Oh, 1 gram. Oh, 1 gram. So by putting in the equation, it's forcing you to think also, I'm not even looking at that, but I'm looking at the scenario and I'm recreating the scenario, mass times the specific heat, right? Times the change in temperature. So it's really making me think what each thing means, right? Time to change in temperature. Time to change in temperature. Okay, plus the mass times the heat of vaporization times the conversion plus the mass times the specific heat of water times the change in temperature. Right, everything good? Okay, now go. Of course, it's doing what we did. Gave it a real result of 97. Oops. Oh, decimal, yeah. So I think on the top, it just gives it to you, and if you want to see the steps, you can scroll down. So 20.188, same answer? Is that what we got? Yeah. Okay, nice. Okay, so now we can change something. We can say, well, what if there was more ice? So you could have, this could really help you too in a book type problem or my test type question, because you'll say, part B might say, well, what if there was more ice? Then you don't have to redo it. If you already have the equation, then you can just change one of the things, right? So let's just say there was, let's just change the ice, for example, from 20 grams to 2,000 grams. So big chunk of ice, right? So that's gonna be 2 kilograms of ice. So then we can just go and just say 2,000. And keep everything else the same, right? See the power of that way of doing it? And then you just go like that. Oh, see now, we didn't make an algebraic mistake. So I was wrong to say, if you get anything less than negative 15, you did the mistake. No, I'm wrong. It's giving you negative 82. The solver is giving you 2,000. I changed this to 2,000, 2,000. Everything else is the same. I'm not even making any mistake. And the calculator is giving you negative 82.3. So any answer that is probably less than 0, even if it be less than -15, it could be that it's not your mistake. So now, obviously we have to redo this. This is obvious, right? If it was between 0 and -15, it's not obvious that you have to redo it. You might think that the answer is right, but I still say you have to redo it. Any answer from here to here, you have to redo it. So we can say here, any answer less than 0 or equal to 0, or any answer greater than 100. So then how would we redo it? What would we have to change? So that's the next question, is determining, once you determine that it's something you have to redo, then how do you redo? So most likely what should happen if you have a lot of ice is the ice should slightly warm, maybe reach all the way to 0, but maybe not, we don't know yet. So assume it doesn't reach 0. It slightly warms and then reaches somewhere here. You know, it could reach 0, but I'm not sure. So you first assume that it doesn't reach 0, and then see if you get a reasonable solution. And if that doesn't work, then that means it reaches 0 and some of it melts. You see? So then how would we redo it if it reaches somewhere here? Then we wouldn't have this, right? We wouldn't have this. Basically, we wouldn't have any of that, right? So how would we rewrite the equation? Well, what I could do to rewrite it is I could just go 2000, 2.108. What should I write instead of 15? TF minus -15, right? TF minus -15, which is just TF plus 15, right? Don't include these two, gone, and then that's the only thing that's gaining heat. See, that's the only thing that's gaining heat now. So that's equal to everything that's losing heat. So now, what do you change here? Where the water starts at 50, 4.184 equals to what? So now the water is gonna lose heat, and then freeze, and go all the way to TF, you see? So the water has to get to that point. So when it's going from 25 to 0, you just put here 25, right? Plus, when melting, how much heat does it lose? Then it goes the mass times the heat of fusion times what? Or change it to joules. That's during the freezing process. The water has to freeze, right? Then what does it need to do? Cool down all the way to TF. So then plus what? 50 times the heat of, specific heat of ice, times what? What's the change in temperature? TF minus 0. But no, I should put it as a, if I want to do it as a positive, what should I do? Because TF is, I'm expecting a negative number. If I put TF minus 0, it's not going to work. That's an algebraic mistake, because this number is a negative, and I should do absolute values, right? So I should do negative TF. You see, that's a little bit of a tricky point, because you're expecting an answer between -15 and 0, right? So if I want this to be positive, I want it to be, if the TF is negative, I need a negative of a TF, so that this is a positive, okay? So then that's the heat lost by the water. How about the aluminum? Then I have this guy, 100 times 0.9 times what? Well, aluminum has no phase change. You see, just because water has a phase change at 0, aluminum has no phase change. So it goes directly from 80 to TF, right? So it's just 100 times 0.9 times, how should I write it? Should I also write TF minus 80? No, 80 minus TF, because if I do TF minus 80, it'll be negative, right? So 80 minus TF, and then of course if TF is negative, then that means 80 minus negative, it's gonna be greater than 80. Yeah, which it should be greater than 80, right? So what else is left? So then plus, then you got all this, steam. So in other words, the equal sign goes over here, all the way here. So the steam you still have, and you gotta condense the steam, then how about the rest? Once the steam is condensed, it's gotta go all the way to 0, right? So I just put 100 here. Oh, wow, this is a lot, huh? It's an easy problem, but not easy, you know, because you have to account for everything. So you gotta condense the steam, then the steam has to go to 0, then the steam has to freeze. So I have to add to this 1 times 79.6 times 4.184. Freeze the steam. Well, I mean, it's no longer steam, but freeze the water. Then what? Then add, then change that to 1 times 2 point, what was it? 108, negative TF, right? Which goes down to TF.
The one is that you have 1 gram steam?
1 gram of steam, yeah. Okay, now let's put that into the solver, change a couple stuff. So let's go back to solver. I don't have these two, right? So,
And why do we assume that it's just 1 gram?
why did we sue? Well, that was the original problem, remember? So all I did is just change the ice from 20 grams to 2,000 grams and say what's gonna be the answer now. So now I just go, where was this X? Oh, cancel this. So is there only one thing here? And then what should I change that to? 2,000 there? TF plus, so X plus 15, right? X plus 15. Then that's equal to what? 50, 4.184. Change this to what? 25 plus what? 50 times what? 79.6 times 4.184, the conversion, plus what? 50 times 2.106 times what? Negative X. That negative X is kind of a tricky part, right? 50 times 2.106 times negative X. Okay, plus the aluminum, which is this one, right? The 100 times 0.9 times what? 80 minus X. 80 minus X. Okay, now instead of equal, so add to it steam. This part is stay the same, 5.39. So then go all the way from 100 to a 0, right? Plus, freeze the steam. Right? Plus, take that frozen steam and take it all the way to TF. So 1 times 2.106 Okay, go! Solution. Here's the moment of truth, drum roll. Yep, meaningful answer, then that's the answer. Negative 7.05. You're probably like, damn, if the test has one of those, it's like the whole test takes that. Right? Probably, most likely, if the test does have that, I won't have as many things, you know. Maybe they'll just have aluminum and maybe steam, so not as many things. But this problem is like a good example of, okay, what can happen? In what case do you have to redo it? And then what do you change in any of those kind of calorimetry problems? Oh, okay, here's the sign-in sheet. Add your name to the bottom if your name is not there yet. And then sign in where it says put your initials, or sign in where with the date for today. Okay, so now the next topic we're gonna get into is the blackbody radiation, okay, emitted from an object. This topic has two major subparts. In Physics 102, you focus on one of those parts in blackbody radiation, and the other part you study more in Physics 103, the modern physics part. The one aspect is when something radiates electromagnetic radiation, what's the peak wavelength that it radiates in, right? So we all are radiating heat from our bodies depending on our temperatures, but we radiate in the different wavelengths of the electromagnetic spectrum, right? Objects that are at room temperature, whether it be us or the earth or anything that's around 300 Kelvin, we will radiate infrared mainly. So that's our peak wavelength, right? And then as we start to heat up, we will start to radiate maybe in the visible spectrum, such as stars, right? You could have a red-looking star, blue-looking star. So that topic is called blackbody radiation.
That's classic Kiledjian.
You see, so the idea of this blackbody radiation is that here, this is the blackbody radiation curve. This is plotted in terms of, usually they plot the wavelength here, or you could plot frequency. Either way, the opposite. And this is the wavelength of the electromagnetic spectrum that you are radiating, right? So it looks something like this. So you can see here, this is a red color star. Temperature is, can't even see that. I think it's like 4,000 Kelvin. This is 6,000 Kelvin. This is a good one. Let's see. So this is an object that is 3,000 Kelvin down here. This is 4,000 Kelvin. So 3,000 Kelvin object is radiating, peaking at 724, so infrared. So in order for you to get to the first, what was that? The first, maybe the radiation from my finger. Right, so in order to radiate in the visible spectrum, you have to be 4,000 Kelvin, right? So of course we are 300 Kelvin, so we radiate in the infrared even more, Okay, so this one, you're graphing the intensity, I believe, right? Is it intensity? Power density. It's watts per meter cube. Let's see here. Yeah, it's watts per meter cube. So intensity watts per meter cubed. They're calling it power density. Power density. So that's something that is at room temperature is going to go something like this. So this is wavelength in nanometers. So it's going to peak, this is temperature 300 Kelvin. And it's going to peak somewhere in the infrared region. And so there's a formula that tells you that the wavelength peak is 3 million divided by the temperature of the object in Kelvin. And this gives you in nanometers. This is, you study this topic more in Physics 103, the peak wavelength. To explain this into quantum mechanics, to understand and explain why the peak wavelength is that and why does it peter off after that. In other words, at really high wavelengths, the object doesn't emit a lot of radiation. At low wavelength, it doesn't, and it has a certain peak intensity. To understand that, it took quantum mechanics and Planck's constant and all of the quantum revolution, right? So if you are at 300 Kelvin, what's that mean? 300 Kelvin, which is room temperature objects, right? So that's going to be 0, 0 cancel. So that's going to be the 30,000 nanometers. That's going to be this wavelength, 30,000 nanometers. Or you could write it as a micrometer, right? 30,000 nanometer, you could write it as 30 micrometers. Take the decimal, go like this. Is that right? Yeah, 30 micrometer. That's a huge, yeah, that's, I mean, I did like this with my hands, but that's wrong. It's still small, but it's much bigger than a nanometer, of course, right? So that's in the infrared region. So, but now if you are 3,000 Kelvin, which is kind of the beginning of a star. We can kind of call you now a star. You're gonna radiate in the 3,000 nanometer, right? So instead of 30,000 nanometer, you're 30,000. So if I was doing this to scale, it would be, if something is 10 times the temperature of that, this would go 10 times. So it would go literally, break this down into 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now let's do it to a little bit more to scale. So now let's just say this is 30,000 nanometers, right? This would be 3,000 nanometers. And something that's at 3,000 Kelvin, oh, what am I doing? I forgot to divide the 3.
Yeah, that's 1.
3 by 3 is 10,000. So this should be 10,000, and it should be 10 micrometers. But the scale is still the same. So now if you're at 3,000 Kelvin, you are radiating 1,000 nanometers, right? And 1,000 nanometers is very red looking because the visible spectrum goes from about 400 to 750 nanometer, where this is red and this is violet. Roy G. Biv, we call that. red, orange, yellow, green, blue, indigo, violet. So 750 nanometer is slightly here. That means 1000 nanometer is like very reddish, right? So what's the curve of that star look like? So it goes like this, but what other thing happens is that the curve goes up. It peaks here. It goes like this. And it never quite goes to zero, asymptotically reaches zero. So you see what happened? The curve, the peak of that radiation curve went from here all the way to there, but the other thing that happened is it went up, which means what? The area under that graph is much bigger than the area under this graph. So that means as you're warming, not only is your peak going from infrared to red, right? But of course you're emitting a lot more radiation. So in Physics 102, we are more focusing on the amount of radiation that you are emitting, which is the area under the graph. Area is the amount total radiation emitted by object. So instead of focusing on where the peak is, let's now focus more on the total radiation. And that's the Stefan-Boltzmann law. Crazy equations. There's this constant called the Stefan-Boltzmann Constant, which is probably also related to pi, k, which is the Boltzmann's constant, speed of light, and Planck's constant. So this is a universal constant, and it tells you how much an object will emit. So to fully understand it, you need quantum mechanics again, because anything that you see an H in there, that means it's based on quantum mechanics. A full explanation requires quantum mechanics. Anything that requires H, because that's Planck's constant. Okay, so the equation therefore is what? The power emitted, this is the total power emitted, and then they wrote it down here, right? A E sigma T to the fourth. So the A is the area of the object, right? Area, surface area. But of course, this graph is not the total area, because it's the area per unit volume, right? So this equation is the total power emitted by that object. So of course it depends on its surface area, and then times the emissivity constant E, and then that constant sigma which they derived, times the temperature to the power 4. So essentially this is the integral of this equation. If we knew the equation of this graph, we could just integrate it from 0 wavelength to infinity wavelength, take the integral of it, and then the area under that graph would be temperature dependent. So of course something that's 3000 Kelvin, this area is going to be a lot smaller than that area. So the equation turns out to be T to the power 4. So how much more area will this have? If the temperature went from 3000 Kelvin to 300 Kelvin to 3000 Kelvin, how much more area will that have? Well, that's the temperature multiplied by 10. 10 to the power 4 is what? 10 to the power 4, 10,000. That means my picture here is not to scale. This graph should go way up, come down, and the total area should be 10,000 times this guy. right? So something that's 3,000 Kelvin is gonna be 10,000 times brighter than us. Something that's at 3,000 Kelvin, 10,000 times brighter, and it will look red. And that's a star right there. That's a lot, right? So why is it so sensitive to temperature? Well, you have to derive the equations and stuff to understand it. But of course, it's sensitive to temperature on the Kelvin scale, you see. If your temperature goes from 1 Celsius to 10 Celsius, let's just give it a human thing. Let's say your temperature is 37 Celsius, right? And your Kelvin temperature is 310, right? And now let's say you're running a fever of 2 Celsius. That's quite hot. And now your temperature is gonna be what? 312. So you might think, oh, let me take the ratio of the Celsius. No, you can't. You have to take the ratio of the Kelvin. The Kelvin is the one. So if you go from 1 Celsius to 2 Celsius, you didn't double the temperature, no. You barely change the temperature in the Kelvin scale, you see. So if you go from 37 Celsius to 39 Celsius, will you radiate more? Will you radiate more? Yeah. Will you shift from infrared to red? No, that's not that hot, you know. You might feel like you're red, but yeah, you kind of do get red, but that's different redness than actually radiating red. You're getting red maybe because of blood flow, or you know, you feel like you're getting red. It's something psychological. So how much more power do you radiate? You can just take the ratio of the two temperatures. 312 over to the power 4 over 310 to the power 4. So if you're running a fever of 2 Celsius, you radiate that much more heat. So you could first take the ratio of the temperatures in Kelvin and then raise it to the power 4. 1.026. Which means you're radiating 2.6% more electromagnetic radiation. Change that to a percentage, right? Multiply this by 100, 2.6%. So here's what you say. If you are running a fever of 2 Celsius, you radiate 2.6% more radiation. That's why that thing that they put in your ear in the doctor's office, that's what that is measuring. How much radiation your body is giving off. And it doesn't even take a second. They just put it in your ear, and then it tells the reading. Oh, okay. It changes that to a digital reading. So they're measuring how much radiation your body is emitting, dividing it by how much you would emit if you were 37, right? And that's what it's giving you. So if you're running a 3-degree temperature, that's quite high. This would be 313. I don't think there's a simple way we could generalize that. You just have to do the power, because it's a power 4. 313 divided by 310. 3.9%. So about 4% more radiation you're emitting. You see? So it's dependent on the temperature to the power 4, but your Kelvin temperature. Okay? Now, what do these numbers mean? Emissivity E and the sigma. This formula is very important also, of course, for determining temperature of stars. By determining their brightness, we can determine their temperatures. That's the kind of calculations you're seeing here. Very interesting, astronomy related. Oh, this is the equation for this graph. This is the one that I said is you'll study in Physics 103. This is the equation describing this thing.
Why do we
Right.
only care about the 2.6?
Well, it's just a better way of saying it, like just to say, if you're running at 2 degrees Celsius, you emit 2.6% more radiation than to say the ratio of your power emitted is 1.026. To the public, they would like to hear percentage, you know. Like you say, if you get a master's versus a bachelor's, in general, you'll be making 12% more money, which is 1.0, 1.12, but you never say it 1.12. People like to hear, I'm making 12% more money, you know. Something like that. Okay, this is the one that I was saying, if you integrate that, if you integrate this function from 0 wavelength all the way to infinity, you're gonna get that equation t to the power 4. I don't know how. No, I could kind of see it, okay. Oh, they're doing it here, they're showing it. Yeah, yeah, that's how it is. You see here? Yeah, right there. T to the 4th came out. So they're probably doing some kind of a, oh, they're doing an integral over the whole space, right? Over the volume. So they're doing I of, what's nu? What's V there? That's frequency. That's just another way of, where's the ruler I like to point to? They don't have it? Okay, there, I'll just use this.
Pointing sticks over there.
So this means frequency, right? So F cubed. They're integrating from 0 frequency to infinity, which is the same thing as integrating 0 to infinity wavelength, right? So then there's the H, so how did the frequency come about here? They did, probably have to look on the top there. You get the frequency cubed, then they did U substitution, then they got this, and then the t to the 4th came out somehow, or from here. And that's what happened. Okay, but now, not only do you radiate heat, you also absorb heat from the surrounding, right? So if you're hotter than the surrounding, you're constantly radiating heat, you are absorbing heat. But since if the surrounding is cooler than you, you're gonna radiate more than absorb. So that's why your temperature is gonna eventually drop and you're gonna go to equilibrium with your surrounding. If you're cooler than your surrounding, opposite is gonna happen. You radiate less than your surrounding, you absorb, you see. So therefore you're gonna warm up. And then black color, it radiates more and absorbs more, okay? So your temperature increases quicker and it cools quicker. So black temperature radiates the best and absorbs the best. That's the emissivity, you see, the E value. The emissivity of a substance is its effectiveness in emitting energy as thermal radiation. And the usually emissivity goes from 0 to 1. So the surface of a perfect black body with an emissivity of 1 emits thermal radiation at the rate of approximately 448 watts per square meter at room temperature. All real objects has emissivities less than 1 and emit radiation at correspondingly lower rates. So black color object is as close to 1 as you can get, right? These are emissivities of some substances, just to kind of see them and compare them. In aluminum foil, 0.03. So aluminum as far away from a black object as you can get. It reflects, so it also doesn't emit a lot of radiation, it doesn't absorb a lot of radiation. So even on a hot day, if you leave the aluminum foil, it's not gonna get very hot because it's not gonna absorb a lot. You see, it's gonna reflect most of the radiation. So asphalt, for asphalt, it makes sense that it's close to 1. Brick, concrete, copper, 0.04, so copper is on the other side. Ice, 0.97. Also, even though ice is not black per se, it's a very good absorber and emitter of this radiation. So ice melts very quickly. You see, 0.97. So it's not necessarily that it's always 1, the black color that's close to 1. Paint, including white, 0.9. Paper, 0.88. Silver, 0.02. So you kind of see the thing. The snow, 0.8 to 0.9. So the Earth overall has an emissivity because depending on how much surface area of the Earth is filled with snow versus water versus sand, it gives the Earth overall the emissivity. And that's why we're worried if we change the Earth's climate a lot, let's say the ice melts. Not only is that dangerous because the water is gonna rise, because the overall, we're playing with the emissivity of the Earth, right? So it could be a domino effect. If with the snow melts, whatever its usage, it's the average emissivity of the Earth, we're fluctuating it. So by doing that, we could actually warm the Earth even more, which means more will melt, which will affect the emissivity more, which means more will melt, and then so on. So that's why you could have that domino effect where we start something which is very hard to return back. If it is truly something we're starting, if it's something that is a general cycle that the Earth goes through, well then maybe the Earth has a way of kind of balancing and bringing it back. So it's the difference between a stable equilibrium versus an unstable, right? So if it is an unstable equilibrium, then it might have a runaway effect, and we might not be able to recover that. So we have snow. Let's see, what's water emissivity? Oh, water 0.96. Okay, so water is higher than snow. That's weird. And then water is like ice, kind of 0.97. Okay, so then if you're emitting and you're absorbing, depending on your emissivity. So if your emissivity is high, you're emitting a lot of radiation, you're also absorbing a lot of radiation. Okay, so the overall equation then looks like this. The power total is going to be A, E, sigma, and all that. I like the blue one. A, E, sigma, T of the object to the power 4 minus A, E, sigma, well, I'll put the sigma, A, E, sigma, T of the surrounding to the power 4. Why did I put minus here? Well, because this is the total power emitted by the object. Right? So this is how much we're emitting based on our temperature. This is how much we're absorbing from the surrounding, right? So we could do a good example here. We could say, let's say you have a human who happens to be cold-blooded. That means he can't control his temperature. So that's why he's sad, right? So his temperature is 310 Kelvin. the surrounding is 300 Kelvin. Okay? So what is the emissivity of a human? Emissivity of human skin or human body. In medical thermography, we don't encounter the same range of emissivity values because human skin is almost a perfect emitter or blackbody with emissivity that is approximately 0.98. Perspiration and skin blood flow introduce variables that effectively alter. So it's close to 1, right? So emissivity is 0.98, let's just say. So we could say, what is his body surface area? Human body surface area. What is the surface area of an average human? See, problems give us chance to Google things. Surface area of average human. Average body surface area for adult men 1.9. Average body surface area for women 1.6 meters squared. So let's say his area is 1.9 meters squared. So if you couldn't control your temperature and you were radiating and you were absorbing from the atmosphere, how long would it take you to reach the same temperature as your surrounding? That means our body temperature would cool down to 300 eventually, right? Well, it never will reach 300. You know why? Because the closer we get to it, the less the difference between the two, right? This starts approaching this. Therefore, the amount you're emitting becomes less, right? So you never actually reach thermal equilibrium with your surrounding, but you can asymptotically reach it, you see? So I can say something like, how long will it take to reach 1 Kelvin above your surrounding? So that's a good problem to solve. So now we know the area is 1.9. We can factor out the E, which is 0.98. And then the sigma is that constant, right? 5 point, what was it? We didn't write it down, right? 5.68, I think. What was the constant called? Sigma. I think it's just called the Stefan-Boltzmann Constant. 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the 4th. You see, so 5.67 times 10 to the minus 8. So the units of this, of the sigma, is watts per meter squared, Kelvin to the power 4th. Now, because this is Kelvin to the 4th, we can't use Celsius here anymore, right? If it was Kelvin, per Kelvin, we could use Celsius, because a degree change in Kelvin is the same as a degree change in Celsius. But anything, if it's to the power 4, we can't use Celsius. Okay, so we're factoring AE this. Then what's the object's temperature? Well, the object temperature starts at 310, but it's going to start to drop, right? Mm-hmm. So I'm going to say T to the power 4. The surrounding temperature is going to stay at 300. Mm-hmm. Why? Well, because the surrounding is a bigger reservoir. Its temperature doesn't change as easily as yours. So we assume that the surrounding stays at 300. So minus 300 to the power 4. Now that's equal to what? Because you're radiating heat, it's going to cause your, we say dq, negative dq dt. Why? Because this is units of what? Power, which is watts, right? Which is what? Joules per second. Now, why did I put a negative? Well, because you're radiating this much power, it's gonna cause heat to flow out of your body and your temperature is gonna drop over time. So this is the amount of heat that's flowing out of your body, and then this is time, joules per second, right? Now I'm gonna introduce the other equation we learned. What's the other equation? Q is your mass times your specific heat times change in temperature, right? Therefore, infinitesimal amount of heat that flows out of your body will cause an infinitesimal change in temperature, depending on the specific heat that you have and your mass, you see? So I'm gonna put here negative mass, right? dq, negative mass, specific heat, infinitesimal change in your temperature divided by infinitesimal time. So every heat that you're radiating out causing your temperature to drop. I'm assuming if you're a cold-blooded animal and you can't monitor your temperature, right? So this is your temperature change and this is your time. So what am I solving for? Okay, now I can cross multiply. I can take the dt and I can put it into here. I can say 1.9.98 times 5.67. Take the dt and cross multiply, put it here. And take this and put it under the temperature. So I took this thing and I brought it under the dt, which is temperature. And this is also temperature, right? dt over t to the fourth. Then I can integrate this. This is officially our first integral in this class, okay? I can integrate this from 0 to t, and I can integrate this and to find the time that it takes for you to cool down. You see? So what is your initial temperature?
Temperature.
310 Kelvin, all the way to 301. Because you never will reach 300, right? And then, of course, if your mass is larger, it's gonna take you more time, right? So for the same surface area, a person that's heavier, it's gonna take them more time to cool down. And the more your specific heat, the more it takes longer to cool down. Wait, if your specific heat is large, yeah, because that makes sense. If your specific heat is large, that means it's harder to change your temperature, right? And so it would make sense that the larger your mass, the more your specific heat, the more time it takes for you to, okay, so now let's take this, let's Google specific heat of the human body. Specific heat of the human body, 3.6 joules per gram, which is, remember, water is 4.184. So we're mostly water, right? So we should be almost as high as water, but of course our bones and our other stuff, specific heat is less. So our overall specific heat, a little less than water. So then I'll give the person a certain mass, let's say 80 kilograms. Specific heat, 3.6. Yeah.
The upper limit for the dt.
Oh yeah, the upper limit for the t is just t, because we're solving for t. Yeah. Okay, so then the rest is 1.9.98, 5.67 times 10 to the minus 8 times t is equal to negative the mass of the person. Oh wait, the mass of the person is 80 kilogram. We gotta be careful here. Specific heat is 3.6 joules per gram per Celsius. So this one we need to change to grams. 80,000 grams is your mass. Or we have to put here 3.6 kilojoules, 10 to the third. You see? So we just have to make sure, because you see here how this is 3.6 kilojoules per kilogram. So if I want to keep it as kilogram, cancel the person's mass in kilogram, but then I have a kilo on the top. So I got to make sure I account for that. So this is joules per gram, and then this one is going to be times 10 to the third. So then that's going to be, then I can change this to kilogram. So kilojoule per kilogram. So kilogram, kilogram cancel. Okay, then times this guy. Temperature over this.
So the negative 2.09
Yeah.
times 10 to the negative 8.
Yep. So what can happen is this negative can actually switch the order of the integral so that you have 301 to 310. Okay, so now you're going to use the integral option on your calculator. Online integral.
Put the thing in the camera.
So you put something like 1 divided by x to the power 4 minus 300 to the power 4.
Oh yeah.
And here goes 301.
Got it.
Yeah. So just she was telling me about the negative.
Right.
She didn't I was confused.
See?
Okay.
Yes.
This is how much you're radiating based on your temperature. This is how much you're absorbing from the atmosphere. So here, don't put 301. That means the atmosphere would be 301. Here you put the atmosphere's temperature, and then here you put the final temperature you want to achieve, 301. Okay, so now, go. Okay, so that's the answer. 2.0909. Okay. It's cool. So this is kind of calculating for us. What are we doing here? We're calculating how many seconds an average human would take to cool down to almost atmospheric temperature if you were a cold-blooded animal and you couldn't control your temperature. Right? So this is 2.0909 times 10 to the minus 8. Then you got to multiply that by 3.6 times 10 to the third times 80. Oh, of course, 10 to the minus 8 here. Now we'll cancel the 10 to the minus 8 here. So you're just left with 2.09 times 3.6 times 80 times 10 to the third. So we have 2.0909 times 80 times 3.6 times 10 to the third over 0.98 times 5.67. And that's going to tell you how many seconds it would take you.
Then in front of the 80, did you make it a positive or?
Yeah, because this negative already I used to switch the integral, and then the integral came out positive. Yeah.
It's 3.6.
Huh?
There's no value.
Oh, it's just 3.6. Seven thousand seconds.
Yeah.
That's what I got. 15 hours.
15 hours. Oh, it's kind of long. I thought it would take. I thought it would go faster. 15.84 hours. Well, because you're 80 kilograms, to cool 80 kilograms is a lot. In 15 hours, you would be, I mean, of course, you won't survive because your body temperature goes down to 27 Celsius. No way, you can't live. Even 1 degree Celsius loss, you have like hyperthermia, you know. So we're built so that we can't go down too much, we can't go up too much. But yeah, it's crazy. Now notice how the answer depends on the different things and see if those make sense. It depends on the integral, which depends on the atmospheric temperature, and of course it depends on the limits, what you're starting with, what you're ending with. The bigger the difference of this, the bigger the integral is gonna come out. So if you wanna go down from 310 to 309, it's gonna take much shorter time, you see. Most of the time it's taking you to cool down is when you're starting to get close to the atmospheric. The first couple degrees, you drop down very quickly, you see? So the other thing it depends on is your mass. The heavier you are, the specific heat, the more you are, the longer it takes. But then on the other side, look at this. These numbers go down to the bottom. So what was the 1.9?
The area.
The surface area of the human, right? So the person that's, if you're the same mass but you cover a bigger surface area, what happens when you're a bigger surface area? You have more to radiate from. So if the surface area is big, it takes you less time to cool down, right? So meaning, if you have a same soup in an open bowl, and then the same soup in a bowl like this, you know, imagine like you have a soup. Usually we drink soup from bowls, right? And you have another soup, and let's say instead of a bowl, you're eating it from a cup that looks like this. Well, which one is better? Well, the soup that's open bowl is gonna cool quicker. You see the bigger surface area, so it's gonna radiate. You see, the same mass. The one that's in an elongated cylindrical bowl actually keeps its temperature a lot longer. So if you wanna like take a thermos like this, cap it, and then bring the soup with you, that's really good because it's a good insulated, and plus the surface area from which to radiate is a lot less. The soup will stay warm. So it just depends what your idea is. If you're trying to eat the soup before going to class and you're home and you want it to cool quicker, then put it in an open soup that's bigger surface area, right? So that's kind of how things get affected. The bigger area, the less time it takes. And then the emissivity. So if the emissivity was lower, let's say, you know, something was like like the aluminum was 0.02. If we were made of aluminum, right? So then it would take a lot longer, right? We wouldn't radiate, we wouldn't absorb, right? So the lower the emissivity, the lot longer it takes. The 5.67 you have no control over. That's constant, everybody has that same constant. So you can't control this. Just the surface area and the emissivity, your mass and the specific heat. So once you can kind of see how things are affecting and why one affects it, makes it bigger, why one makes it smaller, you can kind of see that it makes sense, right? Okay, so the next topic we hit when we come next Wednesday is heat conductivity. This one is heat radiation. So then we talk about heat conductivity and what other topics is in this chapter? This chapter is long. No, I think that's it. Heat conductivity is the last topic in this chapter, and then we do the next chapter, which we do this Maxwell-Boltzmann distribution of gases in chapter 18. So 17 and 18 is quite hefty, a lot of material. Okay, guys, good. So let's take a break around 12.